Hey, video is started. Okay, so this is L4. So now we're doing, thank you for your patience, we're doing L4, translations and stretches of trig functions. This is a good review of translations of models from IB1. Remember, there were different types of translations. So now we will revisit transformations in IB1. In particular, we'll focus on translations.
Vertical.
Yeah.
And horizontal.
Yeah. So quite often you'll hear me call them shifts, but the proper word in IB is translations. In Australia, I think I tend to use the word, shift. Yeah, like vertical shift, horizontal shift. And stretches. Stretches can be. So stretches, like stretch it up, stretch it that way. Good, yeah, vertical and horizontal. So we covered vertical and horizontal stretches and translations in IB1. But we didn't apply them to trig graphs. We applied them to things like quadratics and cubics and all that kind of thing. Particularly quadratics we applied them to, and other sorts of vague functions. So like logs and exponentials and things like that. So you love them. So now we will revisit this. So what do you think that one is? It's just
translation.
Translations.
Transformation, actual maybe.
No, you're right. Translations. Translations are a particular kind of transformations. That's a good question. Good point. Yeah, so transformations is a big umbrella term, and translation is just one type of transformation.
Yeah.
Translations are when a function is shifted horizontally or vertical. So the shape, the width and the height of it doesn't change, it just moves up or down or sideways. A component
is the B.
You were just talking about.
Nah, the stretches are. The stretches come with that. A component vector may be used to represent these shifts. So I actually just snipped this from your IB1 models, a modelling booklet, just to remind you of the fact it's been done. So a component vector may be used to represent the shifts. So -4, what does the -4 represent?
The x, but it actually means 4 to the right.
Yeah, exactly. Oh, hang on.
It's 4 to the left.
Yeah, that's a good point. When it's in the component vector, what you see is what it does.
Okay.
Yeah, but you're right. When it's in the function, the horizontal is the counterintuitive one. So that's right. So needs a shift 4 units left because it's -4. So what you see in the component vector is what happens. So -4 left. Component vectors are always in the form of x and y movement. And a vertical shift of how many units upward?
7.
7 units upwards. So just reminding you, we applied these kind of things a lot to quadratics last year. So that's why I just take the quadratic ones we did. They are in the form of f, x minus c, plus d. So which one is the vertical shift?
The vertical, the plus d.
Yeah, good. The d is good. The vertical shift is the old translation, if you want to say. I'm used to saying shift. What is the c? Good. Horizontal shift. C is the horizontal shift. And that's the one that's counterintuitive. So if in the bracket it said x plus 3, that means it went 3 units left. If in the brackets it says x minus 4, it means it went 4 units right. Whereas the vertical is what it says. So if it's plus 2, it went up 2. If it's minus 1, it went down 1. So for example, this is a quadratic. So let's assume that the regular one, the original one, was just x squared. So the translated one, is that a horizontal or a vertical shift in this one?
Horizontal.
Good. So it's in the shift is in the brackets. Is it plus 2 or minus 2?
No. Minus 2.
Good, yeah. So that function would be x minus 2 squared. The original one that's drawn is just x squared. It's just there to compare it for you.
But it's square because it's a quadratic.
Yeah, it's a quadratic. What about this one here? Is there a vertical or a horizontal shift? Yeah, so its function would be?
X plus 1.
Yeah, x squared plus 1. So remember, yeah, when it's a vertical, it's outside of the function you get.
Okay, good.
It's inside the bracket when it's a horizontal one. And when it's a vertical, it's just a constant term added on at the end. The next one has both.
Next, x subtract 4.
Yeah.
squared, subtract 2.
Good, yeah. Because it went 4 units right. And counterintuitive, so make it x minus 4 in the bracket. And it went 2 units down, so that one's got to follow the pattern. So and these are going to apply to the trig graphs as well. So that's why I'm quickly reviewing this, just to show you that this is something we did do in IB1. I just snipped this from the IB1 booklet we did. And then we're going to apply it to trig graphs. What do you think I'm going on about here? Something starting with X? Stretches, yeah.
Oh yeah,
Stretches. Can be horizontal or vertical. Can you remember what kind of function this original function is? It's called the something function.
absolute.
Yeah, that's right, the absolute value function. It's like a linear that's just been made positive. So the red one, what kind of so they've given you the thing, it's 2x. Is that a vertical stretch or a horizontal stretch? Vertical. Oh yeah, I should have defined it down here. The A, the number at the front is the vertical, means vertical stretch. So the number at the front is the vertical stretch of scale factor A. So the A is the scale factor of the vertical stretch. And it's in the brackets, and it's a number times by the x. Yeah, good. So notice the horizontals are always in the brackets, and it's always counterintuitive. So the scale factor, so it's a horizontal stretch. The scale factor is not B, but it's something to do with B. Scale factor, does anyone happen to remember?
Yep.
It's not exactly B. When it's vertical, it just matches that one. What would be the scale factor? I have to remember. 1 over B, like the reciprocal of B.
Yeah, so it's 2, it would be 1 over 2. And
Yeah,
if
exactly.
it's 1 over 2, I mean, if it's 0.5.
There's like you just scroll up a second.
Yeah, it shows it. I can scroll right up now.
Okay, thank you.
There we go, good. So that was just pointing out what they're in the form of. So the vertical stretch is the number multiplied at the front. B is the 1 over B is the horizontal stretch scale factor, and it's times by the x in the brackets. So this one, what kind of stretch has gone on here? That's what I asked before I
Vertical.
explain. Okay, good. Vertical. What's the scale factor?
2.
Good. Yep. So vertical stretch.
Because it went up.
Yeah. So it stretched it upwards. Yeah. Sometimes they look quite similar, vertical and horizontal stretches of scale factor 2. So that's why it made it narrower. So it's the same one, it's just been made narrower. Vertical and horizontal stretches look quite similar, to be honest, on the graph. But in the function, they appear in different spots. So the original function for this one is a quadratic, x squared, so the middle one there. So notice, where is the number that's been added in? Is it in the bracket or outside the bracket? And so is it horizontal or vertical? Or
Horizontal.
Yeah.
40,
So it's a
Because
horizontal.
it affects the width.
And yeah, right? Yeah, good, exactly, yeah. So horizontal stretch of scale factor. What's the scale factor for the orange one? Good, yeah, 1 over 0.5. Or 1 divided by 0.5 is like 1 divided by a half, which equals 2.
1 times 2 and 1 is 2.
Yeah, exactly, good. So the orange one is a horizontal stretch of scale factor, 1 over 2. Whereas the light blue one, it's still a horizontal stretch because the number's inside the bracket. And what's the scale factor?
0.5.
Yeah. Good. 1 over 2. Because it's 2 in there. So horizontal stretch of scale factor 1 over 2. So see, they look quite similar. Like, because really, if you expanded this bracket, 2x times 2x would be 4x squared. So it could, at the same time, if you expanded it, call it a vertical stretch of scale factor 4. Because it's 4x squared overall. And this one could be seen as a vertical stretch of scale factor 0.25. So really, that's why horizontal and vertical stretches kind of are quite similar. depending on the way you look at them. So now let's apply this to the triggy stuff. What page are we on? What page is it? My goodness. 22, thank you. I'm right up. There it is. Page 22. Okay, so now we're going to try to apply this to triggy graphs. Are we? No. We're on there? Yep, here we are. We're going to apply this to triggy graphs. So far, the general equation for sine and cosine graphs have been y equals a, like a number, like 3 sine bx, or y equals a cos bx. So this stuff you were kind of like covered a bit in GCSE, but I'll remind you of it now anyway. The value, yes, sure thing. The value of a is the Okay. The value of a is the amplitude. Oh. The value of a is the amplitude. So the value of a is the amplitude. It basically tells, yeah, a is like 3 sine x, the amplitude would be 3. Yeah, so the value of a, and if you didn't notice, this is fine, because I'll just explain it as if it wasn't done before. So the value of a is the amplitude. It tells us what the something. Yeah, because it's like you know when we said 3x squared, that means a vertical stretch of scale factor 3. It tells us what the vertical stretch scale factor is. So that's right. If you have a regular sine x graph, and if you make it 3 sine x, it's the same width. It's just vertically stretched up and down. So the value of a is the amplitude. It tells us what the vertical stretch scale factor is, because it's just a number multiplied out the front. Now, in terms of what the b is, a lot of people, the most common error is people by mistake think that b is the period, but b helps you calculate the period instead. The formula for the period, it's not b. It's 2 pi over b if it's in radians, or 360 degrees over b if it's degrees.
Yes.
Yeah. So the period kind of almost tells you how wide the graph is, how stretched horizontally it is. So the period, the value of b informs us of the horizontal stretch. It's not exactly the horizontal stretch. But remember, when you do work out a scale factor for a horizontal stretch, it's always 1 over b. So notice that that's why b is in the bottom, because it's like related to the reciprocal of b. So horizontal stretches are related to the reciprocal of b. So specifically for a trig graph, though, it's 2 pi over b or 360 over b. Therefore, the value of b informs us about the horizontal stretch. Whereas for a tan, what would be the formula for the function of a tan, the period of a tan graph? Because remember, tan graphs, their periods are half the size.
Yes, 1/8.
You have to
They're more like pi over b.
Yeah.
Good, yeah, exactly, yeah, 180 over b, like you said, or pi over b, for equals a tan graph. But we'll just, mainly you're going to be doing with modelling and stuff, it's mainly sine and cos, because you don't really model so much for tans. Because they're wacky graphs. Whereas lots of things in nature and the real world do follow these sine and cos graphs. We will now introduce C and D to these triggy functions. So we've just talked about stretches. Now we're going to relate them to, notice I said shifts, but yeah, the official word was translation. Sorry, I just can't get the word shift out of my head because that's what we use in Australia. So the horizontal shift, feel free to change it to translation. Good morning.
You're always like in Australia.
Yeah, I keep going on about it. So the horizontal shift is the value of C. Similar to like the ones we were doing on the previous page where we were applying it to quadratics. The vertical shift is just a constant that gets added on at the end. It's a value of V. Considering this, find the equations of the following graphs. So this is all related to stretches and translations. Fun, fun, fun. Fun, fun. So now you're going to start to see some graphs where there's going to be some numbers added or subtracted in brackets, or there might be a number multiplied. So if there's a number here at the front, other than 1, that informs us of the Amplitude, good, yeah. Or the vertical stretch. Amplitude's like a fancy way, kind of like of saying like kind of like vertical stretch scale factor. If there's a number next to the x, like added or subtracted inside the brackets, what does that inform us of?
Horizontal shift.
Horizontal shift, yeah, good. If there's a number multiplied by x here instead, inside the bracket,
Transformation. Horizontal. And log the period.
yeah, it affects the period of the graph, like which is like similar to the horizontal stretch. And the D informs us of the, if there's a number added or subtracted, vertical shift, yeah. So there's a lot to kind of think about all at once. Considering this, find the equations of the following graphs. Like, is it 3 sine x? So first of all, to find, doesn't look like there's been any shift. There doesn't look like there's been any horizontal or vertical shifts, because it just seems to be from here to here. Would you say, is it a sine or a cos? What one matches it the most? Sine. Where's this one? Sine or cos?
Cos.
Yeah, this one's sine or cos?
Cos.
Yeah, so you kind of got to decide which one's the best to start with. So cos for that one, sine for that one. What about that one? It's kind of interesting.
Sine.
Okay, let's go with sine, sure. Let's go with sine. Looking at it, it could be sine. Some people might say it could be cos, because it could be that, but shifted sideways. Sine, you could say sine or cos. Let's maybe do both for that one, because that one could easily be either. What's its amplitude? Because remember, it's a sine bx. What's its amplitude? 2. Good. How did you get the 2? So yeah, its principal axis is through here, and it goes up 2, goes down 2. To work out what's its period?
You know, whatever it is, 1080.
Good. Yeah. It goes from here to, yeah, good. 1080. I can't read it. So the period equals 1080. Some people by mistake think that that's B. But what is B?
It's 1080 is 2 pi over 180.
Yeah.
Sounds like it's saying that clearly.
Yeah, that's right. Do we use 2 radians or do we use degrees?
Degrees.
Degrees. So yeah. So I keep writing 1080. Yeah, or you can go to 360 over B equals the period. So how do we calculate B?
360 over 180.
Yeah, good. 360 over 1080. So what is our value for B? I'll check mine here. Oh my goodness. What's our value for B? Anyone got a B? Anyone got a B?
They're gonna be.
A fraction's probably a good answer for this one. What's our value for B? A third, yes. It simplifies to 0.3 recurring or a third kind of thing. And notice there's not been any horizontal or vertical shift, like the principal axis. So long as the principal axis is still there, the x-axis, it hasn't shifted vertically. So long as it sort of begins and ends, starting at the beginnings at 0, it hasn't shifted sideways either. So this one you would just call it y equals 2 sine 1/3 x, or you can go x over 3. So both are fine. 2 sine 1/3 x is also not wrong. Can you see what that was meant to mean? It's Hawaii. So by the way, there's 2 answers there. One is 2 sine x over 3. The other one is 2 sine 1/3 x. Both are okay. I just stopped that one there because I've got to go to another class.
Method that you just thought of.
Anytime. Are you the same answer?
Yeah.
So how did you get your answer there? Got to start.